spark excited resonant transformer. 29. A predecessor to the Tesla coil. 30. Steps in Tesla's development of Tesla transformer around 1891. Sad Smiley 1. Closed core transformers used at low frequencies. 27. Rearranging windings for lower losses. 8. Removed iron core. 9. Partial core. 10. 11. Final conical Tesla transformer. 12. 13. Tesla coil circuits. 31. 32, 33, and Elihu Thomson. 30, 34, 35. Electrical oscillation and resonant air core transformer circuits had been explored before Tesla. 36, 35. Resonant circuits using Leyden jars were invented beginning in 1826 by Felix Savary, Joseph Henry, William Thomson, and Oliver Lodge. 37. And Henry Rowland built a resonant transformer in 1889. 30. Elihu Thomson invented the Tesla coil circuit independently at the same time Tesla did. 38, 39, 40, 29. Tesla patented his Tesla coil circuit April 25, 1891. 41, 42, and first publicly demonstrated it the 20th of May, 1891, in his lecture Experiments with Alternate Currents of Very High Frequency and Their Application to Methods of Artificial Illumination before the American Institute of Electrical Engineers at Columbia College, New York. 43, 44, 33. Although Tesla patented many similar circuits during this period, this was the first that contained all the elements of the Tesla coil: high voltage primary transformer, capacitor, spark gap, and air core oscillation transformer. Modern day Tesla coils. Modern high voltage enthusiasts usually build Tesla coils similar to some of Tesla's later two-coil air core designs. These typically consist of a primary tank circuit, a series LC, inductance capacitance, circuit composed of a high-voltage capacitor, spark gap, and primary coil, and the secondary LC circuit, a series resonant circuit consisting of the secondary coil plus a terminal capacitance or top load. In Tesla's more electric discharge showing the lightning-like plasma filaments from a Tesla coil discharge, Tesla coil interim, advanced, magnifier, design. A third coil is added. The secondary LC circuit is composed of a tightly coupled air core transformer secondary coil driving the bottom of a separate third coil helical resonator. Modern two-coil systems use a single secondary coil. The top of secondary is then connected to a top-low terminal, which forms one plate of a capacitor, the other plate being the earth, or ground. The primary LC circuit is tuned so that it resonates at the same frequency as the secondary LC circuit. The primary and secondary coils are magnetically coupled, creating a dual-tuned resonant air core transformer. Earlier oil-insulated Tesla coils needed large and long insulators at the high-voltage terminals to prevent discharge in air. Later Tesla coils spread their electric fields over larger distances to prevent high electrical stresses in the first place, thereby allowing operation in free air. Most modern Tesla coils also use toroid-shaped output terminals. These are often fabricated from spun metal or flexible aluminum ducting. The toroidal shape helps to control the high electric field near the top of the secondary by directing sparks outward and away from the primary and secondary windings. A more complex version of a Tesla coil, termed a magnifier by Tesla, uses a more tightly coupled air core resonance driver transformer, or master oscillator, and a smaller, remotely located output coil, called extra coil or simply the resonator, that has a large number of turns on a relatively small coil form. The bottom of the driver's secondary winding is connected to ground. The opposite end is connected to the bottom of the extra coil through an insulated conductor that is sometimes called the transmission line. Since a transmission line operates at relatively high RF voltages, It is typically made of 1 diameter metal tubing to reduce corona losses. Since the third coil is located some distance away from the driver, it is not magnetically coupled to it. RF energy is instead directly coupled from the output of the driver into the bottom of the third coil, causing it to ring up to very high voltages. The combination of the two-coil driver and third coil resonator adds another degree of freedom to the system, making tuning considerably more complex than that of a two-coil system. The transient response for multiple resonance networks, of which the Tesla magnifier is a subset, has only recently been solved. 45. It is now known that a variety of useful tuning modes are available, and in most operating modes the extra coil will ring at a different frequency than the master oscillator. 46. Primary switching. Modern transistor or vacuum tube Tesla coils do not use a primary spark gap. Instead, the transistor S or vacuum tube S provide the switching or amplifying function necessary to generate RF power for the primary circuit. Solid-state Tesla coils use the lowest primary operating voltage, typically between 155 and 800 volts, and drive the primary winding using either a single, half-bridge, or full-bridge arrangement of transistors, MOSFETs, or IGBTs to switch the primary current. Vacuum tube coils typically operate with plate voltages between 1500 and 6000 volts, while most spark gap coils operate with primary voltages of 6,000 to 25,000 volts. The primary winding of a traditional transistor Tesla coil is wound around only the bottom portion of the secondary coil. This configuration illustrates operation of the secondary as a pumped. Demonstration of the Nevada Lightning Laboratory 112 scalar prototype twin Tesla coil at Maker Faire 2008 resonator. The primary induces alternating voltage into the bottommost portion of the secondary, providing regular pushes, similar to providing properly timed pushes to a playground swing. Additional energy is transferred from the primary to the secondary inductance and top-load capacitance during each push, and secondary output voltage builds, called ring-up. An electronic feedback circuit is usually used to adaptively synchronize the primary oscillator to the growing resonance in the secondary, and this is the only tuning consideration beyond the initial choice of variable top-load. In a dual-resonant solid-state Tesla coil, DRSSTC, the electronic switching of the solid-state Tesla coil is combined with the resonant primary circuit of a spark gap Tesla coil. The resonant primary circuit is formed by connecting a capacitor in series with the primary winding of the coil, so that the combination forms a series tank circuit with resonant frequency near that of the secondary circuit. Because of the additional resonant circuit, one manual and one adaptive tuning adjustment are necessary. Also, an interrupter is usually used to reduce the duty cycle of the switching bridge, to improve peak power capabilities. Similarly, IGBTs are more popular in phase application than bipolar junction transistors or MOSFETs, due to their superior power handling characteristics. A current limiting circuit is usually used to limit maximum primary tank current, which must be switched by the IGBTs, to a safe level. Performance of a DRSSTC can be comparable to a medium power spark gap Tesla coil, and efficiency, as measured by spark length versus input power, can be significantly greater than a spark gap Tesla coil operating at the same input power. Practical aspects of design. High voltage production. A large Tesla coil of more modern design often operates at very high peak power levels, up to many megawatts, millions of watts, equivalent to thousands of horsepower. It is therefore adjusted and operated carefully, not only for efficiency and economy, but also for safety. If, due to improper tuning, the maximum voltage point occurs below the terminal, along the secondary coil, a discharge, spark, may break out and damage or destroy the coil wire, supports, or nearby objects. Tesla experimented with these, and many other, circuit configurations, see right. The Tesla coil primary winding, spark gap and tank capacitor are connected in series. In each circuit, the AC supply transformer charges the tank capacitor until its voltage is sufficient to break down the spark gap. The gap suddenly fires, allowing the charged tank capacitor to discharge into the primary winding. Once the gap fires, the electrical behavior of either circuit is identical. Experiments have shown that neither circuit offers any marked performance advantage over the other. However, in the typical circuit, the spark gap's short-circuiting action prevents high-frequency oscillations from backing up into the supply transformer. In the alternate circuit, high-amplitude, high-frequency oscillations that appear across the capacitor also are applied to the supply transformer's winding. This can induce corona discharges between turns that weaken and eventually destroy the transformer's insulation. Experienced Tesla coil builders almost exclusively use the top circuit, often augmenting it with low-pass filters, resistor and capacitor, RC, networks, between the supply transformer and spark gap to help protect supply transformer. This is especially important when using transformers with fragile high-voltage windings, such as neon sign transformers, NSTs. Regardless of which configuration is used, the H transformer must be of a type that self-limits its secondary current by means of internal short circuit. Tesla coil schematics. Typical circuit configuration. Here, the spark gap shorts the high frequency across the first transformer that is supplied with alternating current. An inductance, not shown, protects transformer. This design is favored when a relatively fragile neon sign transformer is used. Alternative circuit configuration. With the capacitor in parallel to the first transformer and the spark gap in series to the Tesla coil primary, the AC supply transformer must be capable of withstanding high voltages at high frequencies. Inductance. A normal, low short-circuit inductance, high-voltage transformer must use an external limiter, sometimes called a ballast, to limit current. NSTs are designed to have high short-circuit inductance to limit their short-circuit current to a safe level. Tuning. The primary coil's resonant frequency is tuned to that of the secondary, by using low-power oscillations, then increasing the power, and retuning if necessary, until the system operates properly at maximum power. While tuning, a small projection, called a breakout bump, is often added to the top terminal in order to stimulate corona spark discharges, sometimes called streamers, into the surrounding air. Tuning can then be adjusted so as to achieve the longest streamers at a given power level, corresponding to a frequency match between the primary and secondary coil. Capacitive loading by the streamers tends to lower the resonant frequency of a Tesla coil operating under full power. A toroidal topload is often preferred to other shapes, such as a sphere. A toroid with a major diameter that is much larger than the secondary diameter provides improved shaping of the electric field at the topload. This provides better protection of the secondary winding from damaging streamer strikes than a sphere of similar diameter. And a toroid permits fairly independent control of topload capacitance versus spark breakout voltage. A toroid's capacitance is mainly a function of its major diameter, while the spark breakout voltage is mainly a function of its minor diameter. A grid dip oscillator, GDO, is sometimes used to help facilitate initial tuning and aid in design. The resonant frequency of secondary can be difficult to determine except by using a GDO or the experimental method, whereas the physical properties of the primary more closely represent lumped approximations of RF tank design. In this schema, the secondary is built somewhat arbitrarily in imitation of other successful designs, or entirely so with supplies on hand. Its resonant frequency is measured and the primary designed to suit air discharges. In coils that produce air discharges, such as those built for entertainment, electrical energy from the secondary and toroid is transferred to the surrounding air as electrical charge, heat, light, and sound. The process is similar to charging or discharging a capacitor, except that a Tesla coil uses AC instead of DC. The current that arises from shifting charges within a capacitor